I would now like to calculate the potential function for two other conservative forces that we encounter all the time: spring forces and gravitational forces. We'll begin with spring forces. So first off, let's begin with some type of coordinate system. Suppose we have a spring, we have a block. This is my point x equal equilibrium, unstretched length of the spring. And now whether we stretch it or compress it, here I'll stretch it. I'll introduce a coordinate function x, unit vector I, and my spring force F is minus kx I, where x can be positive for a stretched spring, force is in the negative I hat direction. When x is negative, negative times negative means the spring force is in the positive I hat direction when it's compressed. So this is a force that's a restoring force, always back to equilibrium. This is an example of a conservative force. And now let's calculate the change in potential energy and then introduce a zero reference point and get a potential function for this force. So the first calculation is straightforward. So if we took our displacement to be dx I hat, and we take the dot product of f ds, we get dx I hat dot I hat is 1 times dx. And that's just the x component of the force, displacement, and minus sign, because the x component of the force is negative kx. And so now, if we were to start our system, so again, for our initial state, let's say that the block from the unstretched position is stretched xi, and our final state, whether it's stretched or compressed, it won't matter, but we'll just stretch it out a little bit more to x final. So now let's calculate the change in potential energy between our initial and our final states. Now recall, there's a minus sign because it's minus w conservative. That's minus the integral x initial to x final of minus kx dx. We have two minus signs. That's our integration variable if you want to see it in all the detail. And when you simply integrate x prime dx prime, you get x prime squared over 2. And so the change in potential energy between these two states is 1/2 k x final squared minus 1/2 k x initial squared. And that's physically meaningful. If I take my system initially and the system ends up in the final state, then what I'm calculating is minus the work done by the spring force on the block as it goes from the initial state to the final state. I'm not talking about the work that an external agent does in stretching it or compressing it. This is explicitly the work done by the spring force on the block as it goes from the initial state to the final state. I introduced the minus sign in our definition of potential energy. And so this quantity represents the negative of the work done by the spring force as the system goes from the initial to the final states. Now, you may have already thought about it, but the reference point that we're going to use is x equals 0, the unstretched length of the spring. And our reference potential at that point will be 0. So our reference point is actually the 0 point for the potential. And then our arbitrary state, we can call this the reference state, if you like. That's probably better than the reference point. Our arbitrary state will be at some arbitrary stretch or compress, and our potential energy function at that reference minus the potential energy at the arbitrary state minus the reference state. Well, if we set xi equal to 0 and x final equal to x, as we have in this expression, we simply get 1/2 k x squared. So the potential energy function equals our reference potential plus 1/2 k x squared. And we've defined that our reference potential to be 0. It could have been anything, but we're making it 0 so that we get a nice function, 1/2 k x squared. And again, it's always worthwhile to plot that function. It's a nice parabola, u of x, x. And you can see down here, that's our reference point. We would now like to calculate the potential function for the universal law of gravity. So let's set up a coordinate system first. And in this case, we're going to make a very special case, although the general result doesn't depend on that. So suppose we have a planet of radius rp, and we have a small object. And initially, our object is a distance r away from the planet. This is our initial state. And the planet has mass of the planet, and our small object has mass m. And this object is moving. Of course, orbits really aren't like that, so we should be a little bit more careful. But our orbit might be some type of hyperbolic section, conic section, and the orbit over here is at some final position. And ri is the distance from the object to the center of the planet as our final is. Now, let's just, because there's a central point in this problem, the natural coordinate system to use is polar coordinates in the plane. And let's just imagine that at this moment, we have the universal force of gravity. Here's our object, and it's being displaced a distance s. So our coordinate system is polar. Let's call r hat this way and theta hat that way. And let's blow up our little displacement in terms of our coordinate system, just so that we see what's happening. So our displacement had a, let's imagine that our little ds vector is pointing like this. And our center point here, we have the r hat pointing radially outward, and the theta hat pointing towards the center. Now, to exaggerate this picture, if this is r, then the arc length here is r d theta. And the difference as the object moves from one point here to a closer point towards the center will be dr. And so our ds vector we can write as a radial piece r hat. Now, I don't put a sign in there because only the endpoints of my integral will tell me whether I was going towards the planet or away from the planet, and r d theta, theta hat. And our gravitational force is minus g mass of the planet over the distance squared r hat. So now what we see is that when we take the dot product of these two forces, r hat dot r hat is 1 in polar coordinates. Why is that the case? R hat dot r hat is 1 because these vectors are in the same direction. The angle between them is 0. And remember that any two vectors that are perpendicular have dot product 0. R hat and theta hat are perpendicular. And so r hat dot r hat is 1. R hat dot theta hat is 0. So we only get minus g mp r squared dr. And that's the first step in calculating our potential difference, because u of r final minus u of r initial by definition is minus the work done in going from the initial state to the final state, which are described by these parameters r initial and r final, of f gravitational dot ds. And now we have actually minus sign in the definition, another minus sign coming from the dot product. And let's make this our integration variable, r prime, r initial, r prime equals r final. And there's going to be a third minus sign because the integral of dr r prime squared is minus 1 over r prime. So there'll be 3 minus signs, 1 from the definition, 1 from the scalar product, and 1 from the integration. And so we get r final minus r initial equals 3 minus signs, give an overall minus sign g, m planet, 1 over r final minus 1 over r initial. So this is the change in gravitational potential energy as my small object goes from some initial state to some final state. What about the potential function? Where should we choose our reference point? Now, so our reference state here is a little bit unusual, and it will be at infinity. And we'll choose as a potential for our reference potential to be 0 at infinity. That means when our imagine initial state very, very far away from the planet. And we'll take as a final state, an arbitrary state, just where the object is some distance r from the planet. Now, we have to be a little bit careful, because in this calculation, our final state must always be outside the planet. And the reasons for that is subtle, but the gravitational force inside the planet is no longer minus g m1 m2 over r squared. So our analysis only applies for r bigger than our planet. And if we put these values for r and infinity in here, we get u of r minus the potential at our reference point, which will be 0, equals minus g m mp. And here's the reason why we choose that reference point. 1 over our arbitrary state is just minus 1 over r. But 1 over infinity, if we use the initial state as the reference point, 1 over infinity is 0, so that's minus 0. And so what we get is that the potential function is equal to our reference potential plus, actually minus g m mass of the planet over r for r bigger than our reference. And that is the potential function for the gravitational problem. But now remember, we're choosing that to be our reference point. And so the real conclusion is u of r equals minus g m planet over r, with u at infinity equal to 0. Now, let's just finish this by saying in words precisely what this means. So if I start my system at infinity, and I end my system a distance r away from the planet, and I calculate the work done by the gravitational force in going from infinity to a distance r away from the planet, I take a minus that sign, so the negative of the gravitational work, then that's what that number corresponds to.